Dear all, now we are going to see dropout regularization technique in deep learning. So, dropout is a regularization technique where a random selection of neurons is temporarily dropped. Certain neurons will be stopped while training during the neural network training phase. So, this prevents neurons from co-adapting too closely. So, whenever many neurons are present, it is coordinated with the easily between the two neurons, so few neurons should be dropped while training phase of the deep learning model. So dropout means training deep learning models for a too long on the same data can lead to overfitting, where the model performs well on training data but poorly on the unseen data. So dropout regularization technique helps to overcome this problem by randomly deactivating a portion of neurons during training, hence forcing the model to learn more robust and independent features. So this is the model dropout regularization. The first picture shows the neural network before dropout. Many neurons are present in between the input layer and the output layer, which is coordinating with each other. After dropout, in the second figure, it is showing that certain neurons are dropped while few neurons are activated and connecting with each other. So other neurons are dropped and it is freezed, by which the input which is fed into the input layer is freely communicating with the hidden layer neurons and easily achieved the output. So why dropout is needed? Dropout is needed because it prevents the network from laying too much on specific neurons, hence improving generalization by training and reducing co-adaptation among neurons. So the key feature of dropout is randomly deactivates a set percentage of neurons in each training step. Works with dense convolution and recurrent layers. Dropout rate controls how many neurons are dropped. Remaining active neurons are scaled to maintain output scalability. Reduces co-dependency among neurons and improve generalization. How it works means a dropout works by randomly running off a fraction of neurons during each training pass. When a neuron is dropped, it sends no output and receives no weight updates for that batch. The dropout rate P determines the probability of removing the neuron. A neuron output H is modified as H dash is equal to H into M, where M dropout mask randomly sampled for each neuron. If M is equal to 1 means neuron is kept, M is equal to 0 means the neuron is dropped. To keep activation values consistent during training, inverted dropout is used, where active neurons are scaled as H dash is equal to H into M by 1 minus P, where H original output of the neuron before dropout, H dash output after applying dropout. This ensures that the expected output remains stable even when some neurons are dropped. Note that during testing, dropout is disabled, meaning all neurons remain active and no randomness is applied. The network uses its full capacity and activations are scaled appropriately to match the expected values from training. So type of dropout regularization. Standard dropout randomly removes individual neurons during training to reduce overfitting. Spatial dropout drops entire future maps in CNN to preserve spatial structure. Dropout 2D by dropout for 3D applies dropout across 2D or 3D future channels for images and volumetric data. Drop connect randomly drops weight instead of neurons, offering stronger regularization. Alpha dropout maintains activation statistics and works best with SELU based networks. Variational dropout uses the same dropout mask across time steps in RNN for stable learning. Monte Carlo dropout keeps dropout active at inference to estimate prediction uncertainty. So why it is useful means it prevents overfitting by constantly altering the network architecture during training. The model is forced to distribute the learning across many different neurons rather than relying on a few highly specialized ones. Ensemble effect. Training with dropout is theoretically similar to training an exponential number of different smaller, thinner subnetworks. Averaging these subnetworks during testing improves predictive performance. Forces independent learning. Since a neuron cannot rely on the presence of its neighboring neurons in any given pass, it must learn useful standalone representation of the data. Thank you.